Last time, we used first-step analysis to give some general recursion tools to understand statistics about the hitting time of a Markov process for a particular measurable set. We're going to apply those tools right now in order to understand the behavior of random walks. We've already discussed the symmetric simple random walk on the integers. Now we're going to talk about biased random walks. A biased random walk is like a simple random walk, except it has a drift. It has a tendency to move more in one direction than the other. That is, if we fix some parameter p, a probability between 0 and 1 strictly, we can consider the Markov chain on the integers whose transition kernel is this. P times the indicator of a step to the right plus 1 minus p times the indicator of a step to the left. This generalizes the simple random walk that we already analyzed, which is exactly the case. P equals 1/2 of this transition kernel. And I didn't mention this before, but we can explicitly construct this Markov chain without reference to any Markov process machinery. Xn can be realized as a sum of independent random variables, xc1 plus xc2 plus xc3, etc., where xc0 is just equal to whatever x we're going to start the process in, and the xc1 and onward are IID, biased Rademacher random variables. That is, they have distribution p times a point mass at 1 plus 1 minus p times a point mass at minus 1. So we're talking about IID sums here, and we might think that we could use the tools from the beginning of this course, the strong law of large numbers and the central limit theorem, to understand some things about hitting times of these processes. And that's an interesting exercise, but we can't get quite the level of detail that we want, which we will be able to get using first-step analysis of these Markov chains. So let B be any subset of the integers. We can use first-step analysis, a la the last lecture, to understand the hitting time, TB, and the hitting location of the set B. Remember that we defined in general a function u of x to be the expected value starting in state x of a function h of the hitting location on the event that the hitting time is finite. Now, if we want to understand the question of the probability that the hitting time is finite, we could take, for example, h to be the constant function 1, in which case u of x is exactly the probability starting in x that you do eventually hit b. But as we'll see, even if we want to understand that quantity, it's going to pay to use more general h's here in the analysis from the start. Now, what we developed in the last lecture is the following theorem, that for this general quantity here, u of x is just constantly equal to that boundary function h on b, and on b complement, it's a solution of this recursion equation. U is equal to QU, where Q is the transition operator associated with this transition kernel. This is a discrete setting, and so that transition operator is given by matrix multiplication. And so we can write that out pretty easily right now. What this recursion says is that u of x is equal to the sum over all y of q of xy, u of y. But in this infinite sum, there's only two non-zero terms. And so that says that u of x is equal to p u of x plus 1 minus p u of x minus 1. In the special case, p is equal to 1/2. This is exactly the recursion that we analyzed 2 lectures ago, that u is equal to the average of its values on its 2 neighboring sites. Now, this is a general 3-step linear recursion, which can be written like this: p u of x plus 1 minus u of x plus 1 minus p u of x minus 1 is equal to 0 for every x not in B. As you are studying on your homework, one can generally solve these kinds of 3-term recursions, and the key to doing so, just like it would be if we were studying second-order linear constant coefficient differential equations, is to write down the associated characteristic polynomial, which in this case will be p lambda squared minus lambda plus 1 minus p, and look for the roots of that polynomial. I won't spend your time explicitly factoring this polynomial, but you should check that it has two very nice roots. The roots are lambda equals 1 and lambda equals what I'll call lambda p throughout this lecture, which is the quantity 1 minus p over p. Notice that in the special case where p is equal to 1/2, this root is also equal to 1. That's the degenerate case. Now, once we've written those down, we can declare that on the set B complement, the general solution of this recursion looks like this. In the non-degenerate case where p is not 1/2, you get a sum of two terms, alpha times 1 to the power x plus beta times lambda p to the power x, where lambda p is that non-1 root there. And alpha and b are two arbitrary constants. Because the function h involved could even be complex valued, for all we know, this alpha and b could be complex valued as well, although in the cases we're interested in, they'll be real valued. In the degenerate case where the two roots are the same, we have that the solution of that recursion is instead this general affine function. And those are part of your homework to prove. Now I want to highlight one kind of sticking point here. It might appear that since these recursions only hold on B complement, this doesn't tell us anything about what the function looks like on B. But of course we do know what the function looks like on B. U is equal to h on B. That being said, in principle it looks like we could have U be h on B and then be this on B complement, and the alpha and B could be chosen at will to be anything that we want. There's no connection between the two. But that's not true. If we look at the recursion here, we see, for example, that if x is a point in B complement, but for which a neighbor is in B, then this recursion for u of x will have one of these two terms be u at a point in B, meaning that it's h at that point. That gives us the connection between the two. And so, in fact, the statement is that alpha and beta will be completely determined by the recursion, at least in some special cases where the boundary conditions will determine the value of the function everywhere. That's the case that we're going to consider here in a moment. But before we get there, let's note one symmetry of the problem that will reduce the parameter space P to half of what it is right now. And that is to just note that the transition kernel Q has the property that Q of minus x and minus y, well, if I just plug in minus x and minus y where x and y were before in that formula and then reshuffle this, this is equal to P times the indicator that y is equal to x minus 1 plus 1 minus P times the indicator that y is equal to x plus 1. And that looks just like the transition kernel for x, except that we've interchanged the roles of P and 1 minus P. So that means that if we can understand the behavior of this process in the parameter range that P is bigger than or equal to 1/2, then we know what happens when P is less than 1/2 as well, just by looking at what happens at 1 minus P for that case and reversing the direction of travel. So without loss of generality, we will therefore make this restriction going forward. Now, just to whet our appetite, we already considered this case. That P was 1/2 in the special case that B was a singleton. And we saw in that case that the process is null recurrent. That is, with probability 1, the hitting time of B is finite. But no matter what the starting point is, the expected value of that hitting time is infinite in that case. So it'll be interesting to see if those same properties persist for P bigger than 1/2 in this biased random walk. Okay, well, in order to see that, we're going to need to determine the alpha and beta in this solution. And let's just note that those are in general functions of the set B in question and the boundary function h that we start with. Now, let's consider the following case. Not a singleton point B, but where B is a doublet. Two separate points where by convention A will be less than B. Canonically, we'll choose A significantly less than B. That is, so that there are some things in between. And we'll usually start our process at a point in between A and B. There is a case where we'll be able to solve this recursion totally explicitly, which is what you're doing on your homework. We're going to see in a few minutes that in that case, there is a very nice relationship between the hitting time of this set B and the hitting times of the individual endpoints A and B separately without reference to the other one. Now, just to be perfectly clear here, what we're asking about, the hitting time of the set containing A and B, is the smallest time n at which xn is in the set A and B, meaning the smallest time n for which xn equals A or xn equals B. Now, here's the interesting point in here. If we start at some point x in between A and B, then we'd like to relate this to the question of which do we hit first, the point B to the right or the point A to the left. Since we were considering the case that P is greater than or equal to 1/2, meaning that there's a drift to the right, we would expect there to be a high probability that we'll hit B before hitting A. And so that's what we'd like to compute. Starting at some point x, what's the probability that we hit B, the one to the right, before hitting A, the one to the left? Notice that if x is not in between A and B, this quantity is obvious to compute. For example, if x is less than the smaller point A, then we have to pass through A to get to B. And so this probability will be 0. If x is greater than or equal to B, then we have to pass through B before we get to A, and so this probability will be 1. So we only care about the value of this function when x is in between A and B. Now, those obvious quantities outside of the interval between A and B actually follow from setting this up in terms of the first step analysis that we did in the last lecture, because we can rephrase this question, what's the probability that we hit B before we hit A, as what's the probability that the first hitting location of the set A and B is B. And we can write that cleverly as the expected value of a certain function of the hitting location of the set AB, in the event that that hitting time is finite, where that function h, which remember just has to be defined on the set AB, is taken to be 1 on B and 0 on A. After all, in that case, this 0, 1 valued function has expectation equal to the probability of the event that it takes value 1, which is the event that x of TAB is equal to B. That is, the event that the hitting location is B, that we hit B before we hit A. So this function u is of the form that we did the first step analysis for, and so we have for x outside the set A and B, u of x satisfies this three-term recursion, which means that it has this form here for some constants alpha and beta. At the moment, I'm taking the case P is greater than 1/2, although we'll be able to recover the case P equal 1/2, which we basically already analyzed, as a limit as P goes down to 1/2. So now we need to determine the alpha and the beta in this case, and because we're doing this for x in between A and B, as we established x outside that interval, the value of u is easy to understand, we can just check what's the value of u on the boundary. That follows the same argument as before. If we start at A, the probability that TB will be less than TA is 0 because we've already hit A right before we start, whereas if we start at B, this probability is 1. Those are our boundary conditions. Thus, to determine the coefficients alpha and beta, we just need to solve this system of two linear equations and two unknowns, which is pretty straightforward. For example, we can solve for beta just by subtracting the two, and we get that beta is equal to the reciprocal of lambda to the B minus lambda to the A, and alpha is equal to negative lambda to the A times beta. And therefore u, which has this form here, when simplified, has this nice expression here. Dividing through by lambda to the A, we can write it in this slightly simpler form here. And I'll just comment here that in the case P equals 1/2, if we take the limit as p goes down to 1/2 of this expression here, we do indeed get x minus a over b minus a. That is, this probability in that simple case is the unique affine function which interpolates between the two values. That's what we would expect in a symmetric random walk, whereas we get this kind of affine exponential function for the biased random walk. Now we can use this formula in order to understand the individual probabilities of TB and TA being finite and their expectations as well. But before we do, let's understand the calculation we just did in terms of a game. In fact, this calculation often goes under the name Gambler's Ruin, because we can understand what's going on here in terms of a simple gambling game, something like roulette. A game where you're going to wager each turn, and there's some probability that remains fixed of you winning or losing, and then you wager again and continue. This is going to be a simplified version of that game, where at each turn you must bet one chip. You don't have a choice whether you bet or not, and you don't have a choice about how much to bet. So in this case, we're going to be playing from the perspective of the house. That is, xn is going to represent the house's fortune in this game, that is, your losses after n plays. And the reason for that is that we're considering the case where p is greater than 1/2. And in most successful casinos, the odds of the house winning are greater than the odds of you winning in any given game. You'll enter the game with some initial fortune x, and because we're playing from the house's perspective here, your fortune is their loss, so x is going to be a negative number. And then you will play repeatedly, winning or losing $1 each bet until you go broke. Now we're going to play a version of the game here, representing this exact calculation we just did, where you make a choice. You enter with fortune x, and you're going to choose some desired greater fortune b, that means a larger negative number b in this context, that you'd like to reach. So you will continue to play until either you reach your desired fortune b, or you go broke. That means you're playing until time n, where xn equals 0, or xn equals b, which is less than x, because both of those are less than 0 in this example. So we'd like to know, how likely is it that you'll reach your desired fortune b before you go broke? What's the probability that you get to fortune b before you go broke? That's exactly the calculation we just did in the case where a is 0. So that gives us this simpler formula here for that. And let's write that in terms of positive values for x and b. X and b are negative, and so their absolute values mean we have to take an extra minus sign, which flips to the reciprocal of lambda p. In that case, the absolute value of x is less than the absolute value of b. And remember that lambda p is equal to 1 minus p over p, which is less than 1, and therefore its reciprocal here is greater than 1. And that means that this is going to be an exponentially small quantity, roughly in the difference between x and b. In particular, let's look at the case where b is 2x. That is, you want to keep playing until you double your money, or go broke, whichever comes first. Well, in that case, this formula here gives 1 minus 1 over the reciprocal of lambda p to the x, divided by 1 minus 1 over the reciprocal of lambda p to the 2x. And the denominator factorizes, and so this is exactly equal to 1 over 1 plus the reciprocal of lambda p to the absolute value of x, which is actually slightly less than lambda p to the absolute value of x. Since lambda p is less than 1, this is an exponentially small number. It goes to 0 exponentially fast as x grows. For example, suppose that p is equal to 0.53. There's a 53% chance that the house wins, which is approximately what roulette tables are set to for most houses. That means that lambda p is equal to about 0.89. And so say you come in with $10 and you want to play until you get to $20. Doesn't sound like that should be too unlikely. Well, in that case, if x is equal to 10, you get here approximately 30%. There's a 30% chance that you can double your money. That doesn't sound too bad. But say instead you come in with $100 and want to play until you reach 200. What's the chances that'll happen before you go broke? Well, in that case, this probability becomes about 6 in a million. I don't know about you, but that's not a game that I'd like to play. Now, gambling aside, we can use this exact gambler's ruin calculation in order to calculate the probability that the hitting time of any one point, for any given starting point, is finite. And here's how. Let's start by fixing B. If we consider the hitting time for the set an A up to B, we've calculated the probability that TB is less than TA. Now, what happens if we let A go down to minus infinity? Well, in that case, the hitting time of A certainly goes off to infinity no matter where we start. X is going to be some fixed point, and if A is getting further and further away on either side, but since A is the smaller one, we're going to let it go to minus infinity. That means that the time to reach A certainly goes up to infinity, and so the probability that TA is finite goes to 0. So that means that we can rewrite this probability we're interested in, the probability that the hitting time of B is finite, as the limit, as A goes to minus infinity, of the probability that TB is less than TA by the continuity of probability measures. So we can now quickly and easily calculate that from our formula. Here's our general formula for that gambler's ruin probability, and we just need to take the limit as A goes to minus infinity there, remembering that lambda p is equal to 1 minus p over p, which is less than 1. We can use calculus to easily check that that limit goes to 1 in this case. So that is to say, for any b and for any x, which remember we're starting between a and b, so this is x less than or equal to b, the probability that starting in x we do eventually reach b is 1. That shouldn't surprise us. We already knew that was true when p is equal to 1/2, and now we've included a positive bias. It's more likely to move to the right. So if we start with an x and a b to the right, the probability of eventually reaching it should only be higher than something which was already 1. So that's not a surprise. On the other hand, what's the probability that we reach a? Now we're going to have to take b off to infinity to compute that. So the event that TA is bigger than TB, that event decreases to the event that TA is equal to infinity as b goes up to infinity, for the same reason. As b goes off to infinity for any fixed starting point x, the chances that we eventually reach b go up to infinity, and that means that this goes to infinity. So this event converges to this one, which of course is a decreasing limit of sets. Therefore, if I start with an x in between a and b, and since b is going off to infinity, that just means starting with an x greater than or equal to a, the probability of this event is the limit of the probabilities of those events. And that's what we just calculated from the gambler's ruin, which again we can easily check from calculus is equal to 1 minus lambda p to the x minus a, which is a number that is not 1, but is strictly greater than 0. There is always some chance that we will not reach A in these biased random walks. Let's just put those together. What we've now shown is that if we're in a biased random walk, that is, the odds of stepping right are p, the odds of stepping left are 1 minus p, where p is greater than 1/2, then for any starting point x, the probability that the hitting time of b is finite, that we do eventually reach b, is 1 if I start with x less than or equal to b, but is equal to this quantity 1 minus p over p to the power of x minus b if x is greater than or equal to b. And in particular, in this setup here, in the case where x is greater than b, so we start to the right of b and are asking, can we move to the left to get to b? There's going to be some positive probability, small potentially, but positive, that that won't happen, that this probability will be positive. And since that probability is positive, it certainly follows that the expected value is infinite in that case. Now that's no different than the case p equals 1/2, where we saw that this was infinite no matter what x and b are. But we still have left open the question here, what if we are moving to the right? We now know that the probability is 1 we will get to b if we start to the left of it, but what's the expected time that it will take to get there? In the degenerate case that p is equal to 1/2, it still takes, on average, infinitely long to get there. But in this case, we'll see that's not true. I'm not going to go through all of the details, but following a very similar analysis of the three-term recursion that we get in the secondary problem where g is equal to the indicator function of the set a and b, and taking the limit in the end, we will find in the case that b is to the right of x, the expected time that it takes to get from x to b is going to be b minus x divided by p minus 1 minus p. That denominator is just 2p minus 1, but it's better to write it like this. So in this case, it's just a linear function of the distance between b and x. That's the expected time that it takes. And of course, the closer p is to 1/2, the higher the slope of that linear function tending to infinity as p goes to 1/2. And if you're interested in seeing all of those gory details, they are spelled out in example 22.51 in driver's notes.